Good day, I'm Norman Wildberger. Today, in this series on Foundations of Algebra, we're going to answer the very important question of what exactly is a polynomial? A polynomial is a fundamental building block of algebra, and in most treatments of the subject, it's introduced only in a vague and imprecise way. But fundamental building blocks of mathematics have to be defined very precisely. So I remind you that the usual idea is that a polynomial is some kind of expression involving an unknown variable or general variable x, or perhaps y, or perhaps a, or perhaps b. And this polynomial is allowed to have various manifestations or different expressions. The idea is that it should be built up just from the three operations plus, minus, and multiplication. So these are all considered polynomials in x in the usual formulation of things. And another approach is to think of a polynomial as a function, something that inputs an x and outputs another number given by an expression like this. Alright, so our approach is going to be a little bit different. Right? So roughly our idea is that a polynomial is a polynumber, but it's a polynumber written in a particular form. In fact, it's a particular form that involves linear combinations of something we're going to call alpha. I'll tell you what alpha is in a second, but here's some examples of the kind of thing that we're interested in establishing. So this will be something like a polynomial. P equals 3 plus 5 alpha plus 27 alpha squared. So it's what we usually think of as a polynomial in alpha. But we'll prefer to write this rather in this more laborious fashion. So instead of 3, we'll write 3 alpha to the 0. Instead of alpha, we'll write alpha to the 1, so that the powers of alpha are increasing from 0 onwards up. That's what a polynomial for us is going to look like. And now I have to tell you how do we connect this to polynumbers? And what is this object alpha? We've made the observation before that a polynumber with just one entry at the top, the degree 0 spot, acts essentially like a number. The arithmetic for those polynumbers is just the same as the arithmetic for ordinary numbers. So the first polynumber that goes beyond that arithmetic is this one right here, the polynumber 0, 1. And that's what we are calling alpha. So alpha for us is just a particular polynumber. That one right there. Alright, then it's easy to check that alpha squared is the polynumber 0, 0, 1. Alpha cubed will be 0, 0, 0, 1. And in general, any power of alpha, alpha to the k, say, will be a string of k zeros and then a 1. That means we can rewrite a general polynumber as a linear combination of these powers of alpha. For example, 2703 can be written as 2 times alpha to the 0. Alpha to the 0 just represents 1. Plus 7 alpha to the 1 plus 3 alpha cubed. We've left out the alpha square term because its coefficient is 0. Here, this polynumber 0, 0, 0, 13, 0, 52 can be written in a rather short way by just ignoring the zeros and writing 13 alpha cubed plus 52 alpha to the 5th. And so we say this is the standard form for a polynumber, or if we want to be more specific, the standard alpha form, where we write out the polynumber in powers of alpha, and we use this convention, alpha to the 0, alpha to the 1, alpha squared, alpha cubed, and so on. And we agree to leave out the coefficients 0, as in this case here. We don't write 0 alpha 0 plus 0 alpha 1 and so on. Except in one special case. The 0 polynumber itself, 0 polynumber right there, we will write that as 0 alpha to the 0. We have to write something, and so that's what we'll write. So you can see one of the advantages of this standard alpha form for a polynumber. Namely, that when the polynumber has lots of zeros in it, we save ourselves the trouble of having to write all those zeros. We're just concentrating on the terms which have strictly positive entries, non-zero entries. So here then is our main definition, that a positive polynomial is a positive polynumber written in standard alpha form. So a polynomial is just a polynumber written in a particular way. So this is then not a new mathematical object. We're still just talking about positive polynumbers, but we're writing them in a new way. We've seen this before, actually. When we started off this series, we defined natural numbers as a string of ones. I hope you remember. That was the definition of what a natural number was. But then, at some point, we changed in practice to writing a natural number, not as a string of ones, but in terms of the Hindu-Arabic system. So now when we write a natural number like 345, we're not writing a whole bunch of ones, we're just writing 3, 4, 5. But really, it's the same mathematical object, just written in a new way. It's convenient in mathematics to have alternate ways of writing sometimes the same mathematical object. So please stop the video now and have a look at these 8 examples and try to figure out which of these are positive polynomials. All right? Have a think. Okay, so the answer is only one of them. The first one is a positive polynomial and the rest are not. Let's see why not. This one here has a negative sign. We so far have not introduced negative signs. All the coefficients have to be positive natural numbers. Later on, of course, we're going to include that as a possibility too, but right now we're just talking about positive polynomials. What about this one? Well, we're being a little bit fussy here. This 4 does not have an alpha to the 0 in front of it. We insist that all the terms have coefficients times powers of alpha. The trouble with allowing something like this is it's easy then to get confused between this number 4 being an actual number or being a polynumber. We want numbers and polynumbers to be different objects, technically. So that's why we're not going to allow this. How about this? This seems to be all right. But it's not, because it's not written out in the standard form. The standard form requires that you start with the degree 0 term, then the degree 1 term, then the degree 2 term, and so on. Well, you might say, well, you could expand this, and you could, but that's not something that we want to do. If you give me an example of a positive polynumber, it better be in the required form. I'm like a computer. Otherwise, I'm not going to accept it. So in other words, I'm not willing to do the work involved in expanding this out and putting it in standard form. The person coming with the object has to do that work themselves. What's wrong with 0? Well, we agree that 0 is going to be written 0 times alpha to the 0, because it's level 0, so it should have an alpha to the 0 in front of it. How about this one? Alpha to the 7 plus 2 alpha to the 4. It's not in the standard form. The powers of alpha have to be increasing. Alpha to the n, alpha to the m, these are variable things. They're not powers of alpha in the sense that we're talking about. They've got to be natural numbers up here. How about 2 alpha to the 4 plus alpha to the 5th minus alpha to the 4? This negative sign means that it's not allowed. Even though we could simplify this to alpha to the 4 plus alpha to the 5, if we did that, then it would be a positive polynomial, but right now it's not. So we're being very fussy. We're being very clear. We're only allowing objects which fulfill the specifications of the definition. This is a very good attitude to have when you're laying the foundations for mathematics. Next time, we're going to talk about factoring positive polynomials or positive polynumbers. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.